Hello, in this video we will look at the Nobel Prize in Physics for the year 1902, won by Hendrik, Lorentz and Pieter Zeeman in recognition of the extraordinary service they rendered by their researches in the influence of magnetism upon radiation phenomena. Two prize winners, there's also two Nobel Prize lectures. The first is by Hendrik Lorentz, The Theory of Electrons and the Propagation of Light, and the other one is by Zeeman, of course, is more on the experimental side. Here, first an illustration. Here you see a light source, and in this case a sodium vapor lamp. It sends away electromagnetic radiation, of course, that passes through an electromagnetic field and falls on the screen. And then you get the Zeeman effect. We will see that later. Here you see that was an illustration schematic. This is a real situation, a real experimental setup. With the lamp, of course, here, these are the magnets, and there has to be a screen, of course, to catch the light. Okay, first, the Nobel Prize of Hendrik Lorentz then. All existing of quotes made by me and summarized. Faraday and later Kerr discovered that light can be influenced by a magnetic field. Zeeman showed that if a light source is placed inside a magnetic field, the spectra shows 2 or 3 lines. This must be or. This light is 3 frequencies instead of 1, but when the magnetic field is absent, only 1. I must however add that this situation is not always as simple as this, and many spectral lines resolve in more than 3 components. Lorentz, following the spirit of his day, stated that the physical world as consisting of 3 types of building materials: first, ordinary, tangible or ponderable matter; second, electrons; and third, ether. Lorentz discussed earlier theories on the ether, the bearer of light, especially the theory of Edlund, mentioning also Lorentz without the T, as you can see, which in the end was not satisfactory. So in the end, the ether theory was abandoned thanks to the work mainly of Einstein. Maxwell thought that light vibrations are changes of state of the same nature as electric currents. We can also say that electrical forces which change the direction extremely rapidly, many billions of times a second, are present in every beam of light. Hertz showed that electromagnetic waves, like X-rays, ultraviolet, infrared, hertz, also radio waves, differ only from each other in their wavelength and frequencies. Lorentz discusses refraction of light, which is connected to the difference in the speed of light in different materials, and why this speed also differs for different colors. All the theories of undulation considered the ether as an elastic medium. There was always talk of tiny particles contained in ponderable substances which could be set in motion by light vibration. They must be electrically charged. This idea of small charged particles was otherwise by no means new. This laid the foundation of modern electrochemistry. Professor Arrhenius has expressed the bold idea of progressive dissociation of the electrolyte with increasing dilution. He got a Nobel Prize too later. So we can conveniently call them electrons, introduced later by Johnstone Stoney. The exact matter in which this co-vibration takes place and what reaction it has on the processes in the ether could be investigated with the laws of electromagnetism. The result consists of formulae for the velocity of propagation and the refractive indices in the dependence on one hand on the vibration period, the color of light dus, and on the other hand the nature and number of the electrons as regard the dependence of the refractive index on vibration period. That is color dispersion. In the prismatic spectrum and in the rainbows we see a demonstration of the fact that the electrons in glass and water possess a certain mass. Consequently, they do not follow the vibrations of light of different colors with the same readiness. If attention is focused on the influence of the greater or smaller number of particles in a certain space, an equation can be found which puts us in a position to give the approximate change in the refractive index with increasing or decreasing density of the body. Thus, for example, it is possible to calculate the refractive index of water vapor from that of water. This equation agrees very well with the results of the experiments. Lorentz, thus without T, at Copenhagen had already arrived at exactly the same result, even though he started from different viewpoints, independent of the electromagnetic theory of light. This formula is accompanied by another which makes it possible to deduce the refractive index of a chemical compound from its composition, admittedly only in rough approximation, as was possible earlier with the aid of a certain empirical formula. The fact that such a connection between the refraction of light and the chemical composition does exist at all is of great importance in the electromagnetic theory of light. It thus shows us that the power of refraction is not one of those properties of matter which are completely transformed by the action of chemical combination. The relative positions of and type of bond between the atoms are not of primary importance as concerns the speed of propagation in a compound. Only the number of atoms of carbon, hydrogen, etc. is of importance. Each atom plays its part in the refraction of light, unaffected by the behavior of the others. In the face of these results, we find it hard to imagine that the forces which bind an electron to its equilibrium position and on the intensity of which depends the velocity of light are generated by a certain number of neighboring atoms. We conclude rather that the electron, together with whatever it is bound to, has its place within a single atom. Hence, electrons are smaller than atoms. Since we learned to consider this as the transmitter not only of the optical but also of the electromagnetic phenomena, the problem of its nature became more pressing than ever. And it is the ether. Lorentz then states that all the experiments on the ether failed. Later, the whole concept of the ether was abandoned. Therefore, that was not already done in 1902. Therefore, skip the parts of the lecture dwelling on its supposed nature. Suffice to say that Lorentz's theory is based on the assumption that the ether does not partake of their motion. Starting with the electrons, these must be permeable to the ether and that each must be the center of an electric and also, when in motion, of a magnetic field. For conditions in the ether, I introduced the equations which have been generally accepted since the work of Hertz and Heaviside. Finally, I added certain assumptions about the force acting on the electrons as follows. This force is always due to the ether in the immediate vicinity of the electron and is therefore affected directly by the state of this ether and indirectly by the charge and the velocity of the other electrons which have brought about this state. Furthermore, the force depends on the charge and speed of the particle which is being acted upon. These values determine, as it were, the sensitivity of the electron to the action due to the ether. I arrived at a drag coefficient accepted by Fresnel and was able to explain in a very simple way most of the optical phenomena in moving bodies. At the same time, a start was made on a general theory which ascribes all electromagnetic processes taking place in ponderable substances to electrons. In this theory, an electrical charge is conceived as being a surplus of positive or negative electrons, but a current in a metallic wire is considered to be a genuine progression of these particles, to which is ascribed a certain mobility in conductors, whereas in non-conductors they are bound to a certain equilibrium position, about which, as already has been said, they can vibrate. In a certain sense, this theory represents a return to an earlier idea that we are dealing with two electrical substances, except that now, in accordance with Maxwell's ideas, we have to do with actions which are transmitted through ether and are propagated from point to point at the velocity of light. Since the nature and manner of this transformation can be followed up in details, the demand that Gauss made for a theory of electrodynamics is fulfilled. Weigert, Larmor, and Poincaré contributed much to the theory. When Professor Zeeman made the discovery, the electron theory was complete in its main features and in a position to interpret the new phenomenon. De Zeeman effect, dat is. Electrons which vibrate within particles of an incandescent substance and being about the emission of light, an isolating electron constitutes, as it were, a minute Hertzian vibrator. As for the force which causes a change in the vibrations in the magnetic field, this is basically the force first observed by Ørsted when he discovered the effect of a current on a compass needle. A noteworthy aspect is the enormous size of the charge of these particles compared with their mass. The relative size of charge and mass to their absolute values. We can at least give an estimate of these, if we combine the results to which Zeeman's experiments led with those which can be deduced from the color dispersion of gases, on the hypothesis that this is the same type of electrons. The charge of an electron is of the same order as the charge of an electrolytic ion. The mass, however, is much smaller, about 1/800th part of that of an hydrogen atom. J.J. Thomson at Cambridge has confirmed these results by a completely different method. At present, we are not concerned with the exact value. The principal thing is that, as we have remarked before, the electron is very small compared with the atom. The latter is a composite structure which can obtain many electrons, some mobile, some fixed. Perhaps it bears electrical charges which are not concentrated at a single point, but distributed in some way. The Russian physicists Egorov and Grigorievsky found that the sodium flame situated between the poles of an electromagnet emitted partially polarized light. The vertical electrical vibrations have a greater intensity than the horizontal ones. The flame has a certain thickness, and that the beam emitted by the back half are partly swallowed up again as they pass through the front half. This absorption effect is the strongest when all the incandescent particles in the flame are vibrating with the same period. The magnetic field does this. Instead of a common period of vibration, it causes several to come into play. However, the increase in illuminating power brought about in this way is restricted to the vertical vibrations in the flame that we are imagining. Now that I have come to absorption, I must all consider the markedly and important theoretical consideration to which Professor Voigt at Göttingen has been led by Zeeman's discovery. His theory differs from mine in that mine is of course Lorentz, that he always has in mind not the emission of light but its absorption. He explains the so-called inverse Zeeman effect, that's the phenomenon that when a strong white light is transmitted through the flame situated between the poles, instead of absorption stripe we get a triplet of dark lines. On the basis of parallelism between absorption and emission, it is possible to work back from this inverse phenomenon to the direct one. Voigt does not refer to vibrating electrons. He is content to add appropriately chosen new terms to the equations which present propagation in an absorbent medium. This method throws into relief the connection between the Zeeman effect and the rotation of the direction of vibration which was discovered by Faraday, and has other advances, namely when vapors of rather high density, which correspond with right spectral lines, are concerned. I prefer to choose the emission from very rarefied gases as an object of study. Here the radiation from the single molecules or atoms, undimmed by their effect on each other, is mirrored by the sharp lines in the spectrum. I followed this course in my later research, but come across considerable difficulties due to the fact that although the simple triplet frequency appears, in many cases there is resolution into more than 3 lines. As long as we have to deal only with resolution into 3 components, it is sufficiently explanation to assume that each incandescent atom contains a single electron which can vibrate around an electron position in all directions in the same way. This simple theory, however, leaves us high and dry as soon as spectral lines split into more than 3 components in the magnetic field. Imagine a light source which shows a Zeeman triplet under the influence of a magnetic field. The 3 lines naturally cannot appear unless 3 types of vibration with slightly different periods are present in a single light source. These periods, however, can only be different in the direction of movement, or the shapes of the path in the 3 cases are not the same. We will say in short that we are dealing with 3 different vibration patterns, each with its own frequency, in the light source. We will now gradually reduce the intensity of the magnetic field and finally let it disappear. As long as even a weak field is present, the free lines persist, only they draw nearer each other. The free vibration patterns thus always exist, but the frequencies approach a common limiting value, the frequency of the unresolved spectral line. In this way, we come to suppose that even when we observe the latter, the free patterns of movement still exist, even though without distinguishing themselves from each other by their frequency, as is the case in a magnetic field. It can be expressed thus: the spectral line is already freefall before the magnetic force comes into play, and this force has nothing else to do except, as it were, to push apart the free lines which originally coincided. The same applies to a 4, 5 or 6 volt line, and you may rest assured that the spectral line will never resolve into 6 components unless, before the magnetic field is set up, each incandescent particle can vibrate in 6 different ways. That is, with the same frequency. A suitable model of vibrating atom would be an elastic spherical shell with an uniformly distributed electrical charge, whose surface is divided into nodal lines into a greater or lesser number of fields vibrating in different directions. It has become apparent that many line spectra are constructed according to a definite type. The lines are arranged in certain series, and in such a way that each series consists of lines which are distributed over the spectrum in accordance with a fairly simple law. Moreover, there are relationships between the one series and the next. Lorentz mentions further the work of Rieberg, Kaiser, Runge and Paschen. He points that the electron theory is also present in other fields, cathode rays, Becquerel rays, etc. He also deals with the now abandoned theory of the electromagnetic mass, which I skip here. Thus we hope that the electron hypothesis, as it is being taken up, will lead to a general theory embracing many aspects of physics and also of chemistry. Perhaps it will be itself completely transformed on the long journey. However, there can be hardly any doubt that our hypothesis about the connection of widely differing phenomena with electromagnetism will prove correct, and that hence, insofar as it relates to the nature of vulnerable metal, that general theory will be an electrical chemical one, as Berzelius already foresaw and as he tried to demonstrate with the resources at his disposal. Well, as said, this was a summary made by me. The complete lecture can, of course, be found at the official site. Okay, then we move on to the second lecture. First, here an illustration of the normal Zeeman effect. Here you have two spectral lines with each, of course, energy level. This is in a situation where there is no magnetic field. If you put the substance in question in the magnetic field, then you see the one energy level is splitting, in this case in 5 and here in 3 levels. Yeah, and later this was connected when the electron theory was further developed by electrons hopping from one trajectory to another. That will come in later Nobel Prizes. Okay, then we go to the second lecture by Pieter Zeeman. Light radiation in a magnetic field. He does more the experimental part. I hope that we will allow me, therefore, to emphasize these experimental investigations. This is a summary and kept apart, as you can see. Two fields of physics, light and magnetism, are combined in the subject of today's lecture. Zeeman points to the discovery of light, magnetism connection by Faraday in 1845, now called the magnetic rotation of the polarization plane. But some of his other, like the 1862 experiments, failed. Maxwell said in 1870 that no force in nature can alter even slightly either their mass or their period of oscillation. A surprising statement. Zeeman entered the field investigating the Kerr effect. The splitting of light of a luminous gas cannot be done by a Newton or Fraunhofer prism, but it can be done using Lorentz concave grating, a polished metal mirror with a very large number of grooves. A beam of compound light is no longer reflected by the line surface in the ordinary way. Instead, each special kind of light follows its own path. One must use a restructured light source, placing behind an opaque screen with a similar slit. The spectral lines produced can be observed, and from the location and intensity of the linear slit images we can determine how the different kinds of light in the being studied are distributed on the basis of the period of oscillation and intensity. The grating is concave, so no lenses are needed. Photography has made it possible to fix these images and provide us with a permanent record of each observed spectrum, which can be measured out any time. Then a barium sodium flame was studied. We see a spectrum consisting mainly of two separate sharp yellow lines, which in our grating lie about 1 millimeter from each other. We see that sodium radiation consists of two kinds of lights, the periods of oscillations of which differ only slightly, 1 in 1,000, from each other. We confined our attention exclusively to one of those two lines. In 1896, Zeeman exposed the sodium flame to a large magnetic force by placing it between the poles of a strong electromagnetic. Again, I studied the radiation of the flame, i.e. Zeeman of course, by means of Rowland's mirror, in the observations being made in the direction perpendicular to the lines of force. Each line, which in the absence of the effect of the magnetic forces was very sharply defined, was now broadened. This indicated that not only the original oscillations, but also others with greater and again others with smaller periods of oscillation were being radiated by the flame. The change was, however, very small. In an easily produced magnetic field, it corresponds to 1/13 of the distance between the two sodium lines, say 2/10 of an angstrom. Had we really succeeded, therefore, in altering the period of vibration, which Maxwell held to be impossible, or were there some disturbing circumstances? Zeeman doubted the result, but after eliminating the disturbance, it was confirmed. We also studied the reverse phenomenon, the absorption of light in sodium vapor, and this too satisfied our expectations. Zeeman at the time confirmed conclusions following Lorentz's theory of optical and electrical phenomena. This theory assumes that all bodies contain small electrically charged mass particles called electrons, and that all electrical and optical processes are based on the position and motion of these electrons. Light oscillations result from the vibration of the electrons. On the basis of Lorentz's theory, if we limit ourselves to a single spectral line, it suffices to assume that each atom or molecule contains a single moving electron. Now, if this electron is displaced from its equilibrium position, a force that is directly proportional to the displacement restores it, like a pendulum, to its position of rest. In this model, the electrons are presented by the red balls and in the direction of the magnetic force by the arrows. Now, all acceleratory movements of such an electron can be conceived as being split up into force, and in two circular oscillations perpendicular to this direction rotating in opposite directions. In the absence of a magnetic field, the period of all these oscillations is the same, but as soon as the electron is exposed to the effect of the magnetic field, its motion changes. According to the well-known electrodynamic laws, an electron moving in a magnetic field is acted upon by a force which runs perpendicular to the direction of motion of the electron and to the direction of the magnetic field, and whose magnitude is easily determined. Here the rectilinear oscillation is not changed by the magnetic field. The period remains the same. On the other hand, the two circular oscillations are subjected to new forces which, running parallel with the radius, either increase or decrease the original central force. In the first case, the period of oscillation is reduced, and in the second it is increased. Now let us consider first what happens in the direction running perpendicular to the lines of force. To the free electron motions, there correspond free electrical oscillations, or in the term of electromagnetic light theory, 3 light oscillations of different periods. Thus the light source will emit 3 color light instead of the original 1 color light. Therefore, instead of the single non-polarized spectral line, we shall see 3 separate lines when we place the light source in a magnetic field. The different directions of oscillations of the electrons affect the polarization state of the emitted light. The light of the middle component oscillates in parallel and that of the outer component is perpendicular to the lines of force. But let us first consider the rays which run parallel with the lines of force. The opposite circular oscillations of the electrons excite 2 circularly polarized rays rotating in opposite directions, one having a longer and the other a shorter period of oscillation than the original spectral line. The original spectral line splits up under the action of the magnetic field into 2 components which are circularly polarized in opposite direction. The light source emits 2 color lights. The magnetic cleavage of the spectral lines is dependent on the size of the change of the electron, or more accurately, on the ratio between the mass and the charge of the electron. When Professor Lorentz published his theory in 1895, no data were available from which to estimate the ratio between the mass and the charge of the light exciting particles, and in this theory the ratio was left undefined. We can now calculate this ratio from the magnitude of the magnetic splitting of the spectral lines. It is 1,000 times as great as a similar number which was known from electrolysis phenomena in the case of hydrogen atoms. This makes it probable for the physicist that in the luminous particles only 1,000th of the atom oscillates, and that is the main mass of the atom remains virtually stationary. The oscillating atoms and the electrolysis ions were found to be not identical with each other. If they had been, the splitting of the spectral lines would have been only 1,000th of what is observed. Are oscillating particles positively or negatively charged? The oscillating electrons are negatively charged. We know that cathode rays are negative particles with some high charge-mass ratio. We conclude that that which vibrates in the light source is the same as that which travels in cathode rays. We have now seen that light can in fact be magnetized, and according to Professor Arrhenius' theory, we have in nature itself, in the northern lights, an example of illumination of the magnetic lines of force of the Earth by electrons escaping from the Sun. It was very quickly found that there are many exceptions to the rule of splitting of the lines only into triplets. The French physicist Cornu was perhaps the first to observe that. Very soon a number of physicists were working in the extended field: Becquerel, Cotton, Michelson, Preston, Ricci, Runge and Paschen. But despite this very complicated splitting up, even when larger aids were used, division into 3 groups of oscillation, 2 perpendicular to and 1 parallel with the lines of force assumed in Lorentz elementary theory remains valid. It was soon able to show that there are great differences in the splitting up of different lines of substance. Particularly great differences were found in lines belonging to different series, discovery of which we owe to Kaiser and Runge. I found very great differences in the lines of different series, and it appeared that the splitting up, contrary to the postulations of the elementary theory expressed in the scale of oscillation frequencies, is not the same for all lines in the magnetic field. We conclude from this, on the basis of Lorentz theory, that the charge-mass ratio is not the same for all electrons. Zeeman then mentions 3 other phenomena, which I skip here, and I is here not Zeeman but me, and a comprehensive view of magnetic optical phenomena of void. Well, these were the 2 lectures. Of course, this is not the last word on the Zeeman effect. There are later a lot of work was done to explain all the different phenomena. There are more. For instance, here we have a transverse Zeeman effect. There are many other Zeeman effects also in the nucleus of the atom, which were all explained in later years. This was it. Thank you for watching, and maybe until another time.